Okay, we're going to continue with our exercise. Can you see my screen, full screen?
Yes.
People? Okay, so this is Bernoulli's equation. In this case, I have the density in the denominator. Please, this is density, okay? This is not a specific weight. We have to be careful. So it's mass divided by length cubed. Now, we still have a minor step to complete because usually we use it like this. We linearize it, okay? So let me go back. Here, we see that this is a velocity multiplied by itself. So this is a quadratic term. So if we say that the velocities are small in general, we can neglect that term, okay? So that's one step. So that's the linear Bernoulli's equation. Okay, so the phi exi is small. So the square is neglectable. So it doesn't appear here. So with this, we can calculate the pressure, and we have this term, which is the most important. And in certain cases, we have to include this one here if we want to consider gravitational waves. And we will see that in a minute. Okay, not today, in the next session. Now, in some cases, we just said, okay, this is a constant, okay? So if you have a body, a closed body, and you consider this term here, that means that you're going to have the same pressure over the body. What's going to be the total force in this direction? Okay, so the total force, if you integrate this, since this is a closed body, the total force is going to be 0. So you're not going to have any absolute term after you integrate this pressure term. So usually just neglect it. In other cases, you can select a reference point in order to find this value. This is the case now, but in general, we just neglect it and that's it, okay? So this is a more simple way if we get rid of this constant, okay? If for some cases we have no gravitational effects, okay? That means there are no waves, okay? Then we just get rid of this. Let's suppose, for example, we are working, see, this is a free surface, right? And we are well down here, and we move like this, okay? But this is very, very low. So basically, rho g x3 is constant over the body. Okay, so it's basically this case. That means that you integrate, since it is a closed body, and the integration will give you 0. Okay, so that's another way of saying that if you are away from the surface, okay, there will be no gravitational effect. If you oscillate here, close to the free surface, of course, there's going to be some wave generation. And in that case, yes, you need the gravitational effect in order to set up the wave characteristics, okay? So in some cases, this is the way we can use it, okay? Now, let's go on. Now, let's do an example, okay? Let's work with an ideal flow. So that means that, see, this is the body, so this is the fluid. Here, all of this is fluid, okay? Now, this body is moving with velocity u. See, it's a steady velocity. So the whole the whole doesn't change in time. Okay, so here I have this equation has to be satisfied inside the domain, inside the fluid. Immediately you see this and you have to consider that, or you have to think that the fluid is incompressible, doesn't change in viscosity, in density, and also there is no influence from viscosity. We are neglecting viscosity in this case, immediately, okay? Now, the solution for this problem, you can find it in several hydrodynamics books. For example, this solution is found in the book by Newman, okay? So let me write it here because it's something that, I mean, it's very famous book or author. Okay, so it's Newman, J, and the title of the book is Marine Hydrodynamics. It's a classical book, okay? We have a couple of copies of this in our library. It's Newman is a mathematician, basically, so it's hard to read, but yeah, it's really, it's a nice piece. Okay, now here you see that U, that's the velocity. R, in this case, the solution is being expressed in polar coordinates, okay? So R theta, as you can see it here, R theta are the polar coordinates. So R is the distance from here, and theta is the distance from the x-axis, angular distance from the x-axis. So this point here has x and y coordinates, but it also has R theta coordinates, okay? R0 as the radius of this circle, of the disk. Theta and R are the polar coordinates, okay? So we assume that this is a solution. Please notice that this is the velocity, units of L over T. And here I have R, which is length. Here I have R squared over R, which is length also. So this is units of length squared over time. So this is correct. So phi has the correct units, okay? Now, we want to calculate the pressure on the body, pressure distribution on the body. But before doing that, I would like you to pay attention to this. You have to check that it indeed satisfies Laplace's equation. We have a boundary condition that we have to satisfy on the body. And there is, in this type of problems, it's always a good idea to check what happens when you are away from the body. Okay, in that case, we should check that indeed there is nothing strange. Okay, okay, please pay attention to this. There is an R in the denominator. That means that if R is very small, phi will blow up. That's typical of this type of problems. We call it singularities, okay? Now, so let's go in steps. First, we have to check that it's indeed this function satisfies conservation of mass in the case of irrotational flow. That means that we have to satisfy Laplace's equation. Oh, now, since we're working in polar coordinates, okay, it's better to express the Laplace's equation in polar coordinates. So this is Laplace's equation in polar coordinates. Okay, So the second derivative with respect to r, 1 over r, first derivative with respect to r, 1 over r squared, second derivative of phi with respect to theta. Okay, that's equivalent to d2 phi dx2 plus d2 phi dy2. This is equivalent in the polar or in the rectangular coordinates. Okay, Manrique, Carrillo, Hidrobo, and Matute, you differentiate twice with respect to r. The rest will differentiate with respect to twice with respect to theta, and I want the results. Enrique, Carrillo, Hidrobo, Matute, and Freire, you differentiate with respect to r twice, and the rest you differentiate with respect to theta twice. Shouldn't take too much. When you're done, raise your hand so I can write your answer. I need first the phi dr, and I'll tell you in a minute why. The phi dr. Do you have it, Miss Hidrobo? Do you have it, the phi dr?
No, yes, on it.
Come on, Mr. Matute, do you have it? If you don't work, I'm going to remove you from our classroom. As simple as that. Please, everybody, turn on your cameras. I don't want to be talking to myself. Everybody on your cameras. If you don't turn on your cameras, Giovanna, please, you see that you can see somebody removing from the classroom.
Okay.
Oh, that's it. Don't doubt it. If you see that I ask somebody and doesn't answer, remove it. That's it. I don't want to be wasting my time. That's it. How many people are we here, please? It's supposed to be 21.
At the beginning, we were 16.
Okay.
16 students.
Okay, Jimenez, you have it? First derivative with respect to r.
R is a u by 1 minus r sub 0 to square over r to square. Close the cosine of theta.
Okay, now the phi d theta. So I need one of these. Ms. Astudillo, do you have it? The first derivative with respect to theta.
Yes, doctor. I have is minus u r plus r sub 0 squared over r sine the theta.
Thank you. So I need these two expressions. You will see that in a minute, okay? Because the derivative of phi with respect to r, that's basically the velocity in the r direction. And this, we divided by r, will be the derivative in the tangential direction. So we need them both. Okay, now somebody, the second derivative of phi with respect to r. Anybody? Okay, do you have it? Vicky, you have it?
I think it's u minus u r0 square divided by r cubic cosine theta.
Is this correct? Anybody?
I think
Multiply by 3.
Or multiply by 2?
Is no minus. It's plus, doctor, 2.
Yeah,
Plus
2.
2.
Plus, multiply 2.
Okay, that's that. So that's this term here. We have this in here. The second derivative with respect to theta. Mr. Iñiguez, second derivative with respect to theta.
Sorry, doctor, no, I don't have yet.
Come on. Mr. Barba, second derivative of phi with respect to theta.
Yes, es minus u.
Let me put this in front of here, minus u.
Okay.
Okay.
Minus u por r más r over r close cosine.
There.
Yeah.
So we have that, and we're missing this term here. So we have 1 over r. The phi dr is going to be, this one here is going to be u over r, 1 minus 0 squared over r squared cosine theta. So you have to combine these three terms, and they have to check that they are indeed 0. Okay, so the minus 1 here, minus 1 over r cubed. I have another one here, so that's 2, and here I have 1 positive, so that's cancel this and cancels that. And I have this one here, u over r cosine. I have minus u over r cosine, so that's that, that's 0. Okay, so that proves you that it indeed satisfies Laplace's equation. So this is, as far as the Laplace's equation, this is a correct function for this problem. Just the first step. Now, second, we have to satisfy boundary conditions. Okay, now this, okay, this is solid. Because this is a body. So we cannot have any fluid crossing the surface of the body. And for that, we are going to satisfy the boundary condition on the surface. Okay, so we are going to evaluate the velocity on the body, okay, and here. And we cannot have this component. Okay, if we have velocity component in the direction r, that means that the fluid is crossing the surface. So the body is not fluid, it's not a body anymore, right? Because the fluid is entering into the body. Now, we could have velocity tangential, but we cannot have velocity in the normal direction on the body. So to evaluate that, we know that the velocity is nabla phi, and that's in the case of the polar coordinates is d phi, dr in the r direction plus 1 over r d phi, d theta in the theta direction. Okay, so in any point here, for example, you have the velocity in this direction and in this direction. So this is going to be Br, this is going to be B theta. Okay, Br is simply d phi dr, and B theta is equal to 1 over r d phi d theta. Okay, this is the unit vector in the r direction, and this is the unit vector in the theta direction, the tangential direction. Okay, so we want to calculate d phi dr and evaluate it on the surface. That's why I asked you to calculate. Here I have 1 over d phi dr. So the phi dr is equal to u 1 minus r0 squared over r squared cosine theta. Evaluate it now. Evaluate it at r equal r sub 0. You see, r equal r sub 0 is the surface of the body. So if we evaluate this at r equal r sub 0, what do we obtain, people? What do we obtain?
0.
0. 0. That's what we expected. This is what we call no penetration boundary condition. Okay. It's very interesting. Right now, we have one of our graduates is doing doctoral studies at the University of Ghent in Belgium. And he's doing a study on the flow. When the ship gets closer to the port in Rotterdam, Belgium, they navigate very close to the bottom. And the boundary condition on the bottom, usually we say is d phi dz is equal to 0. So there is no velocity crossing the bottom surface. But the problem with these ships is that the bottom is not really solid. It's like a mud. So they have to consider a different boundary condition for the bottom of that port. So they're doing a lot of studies in order to, because he explained it to me that the difference in boundary conditions generates a completely different result. I mean, the waves which are generated are completely different. So this is correct. So we indeed have a body because there is no fluid coming inside the body. Fine. What else? Now, let's prepare a scheme of lines of constant velocity potential. Okay, so we have to write in here, in the domain, lines where phi is constant. okay? And the way I do it is this. I can rewrite this, okay? Like this. And what I do is this. I fix theta. Okay, well, first I fix phi. Okay, so I get phi, set phi. Okay, so I'm going to write a curve on which phi has this value. Then what? Then what I do is I choose theta. And for that direction, theta, I solve this equation, R. And then repeat the process. So for example, I have phi, that's fixed. I choose the theta, that one, and I solve this equation for R. So let's suppose I found this value. So in this point, the function phi values the value that I chose it up here. What do I do next? I change for a different value of theta. So I look for a solution for a different value of theta. Let's call it theta 2. So after finding this, I solve this equation and I found another value of R. So now let's suppose the solution is this. And again, I do it and I find another value up here. So around this curve, the function will value this. We'll take this value. Okay, that's what I have done in here. So I chose, for example, a value of phi equal to 0.5. So I get theta and I got points. Then I change the value of theta to 0.35. And again, I'm changing the values of theta. And for each value of theta, I find the value of R. And I got these values of this orange curve. Then I find values for the green, etc. Now, these are values of phi constant. And I have to remember now that the velocity is nabla phi. Geometrically, what does that mean? Anybody from your vector calculus, what does that mean? That the velocity is nabla cross phi.
They are perpendicular vectors?
They are perpendicular when phi is a constant. So that means that B is perpendicular to lines of constant so we can see up here, see, this is basically vertical. So basically we're saying that we are going, if we get closer, you see that there is some inclination, right? So it's like going like this, a little bit inclined, a little bit inclined. There. If we get closer, you see that I have this velocity, and here definitely I'm inclined, and here there's something like that. You see that it is getting around the disk. Okay, how did I do it? First, I did a draw of the lines of phi constant. And then with those, I can specify more or less the lines of the velocity. And you can see that that's should be, right? Because we're considering that we have a circular section and we are around, we're going around, the fluid is going around the body. Okay, so right now we're ready. Okay, we have checked that indeed we satisfy Laplace's equation. That means that conservation of mass is satisfied considering that there is no viscosity. We have checked that there is no penetration through the surface body. Now what we have to do is calculate the other component of the velocity. And that component is the tangential velocity. Let me go back. Here, I have the phi d theta. Okay, so the phi d theta, it's equal to r, that's u, r plus r0 squared over r sine theta, and it was negative, right? That's equal to minus u, I have 1 plus so if I am up here in this region, okay, what type of fluid motion would you expect? Well, I would expect that this moves like this, right? Because I'm away from the body. So let's evaluate this in this region. What value, more or less, would be for theta in this region? More or less. Theta would be value of what? Ms. Hidro, what value of theta would we expect for this area? For a point in this area? What value of theta would you expect?
It's a small value, like
Yes, because you draw something like this, and this is going to be the theta. So it's going to be very small. So how much is going to be the sine of theta if theta is very small, Ms. Hidro?
the time.
Very small, because the sine of 0 is 0.
Yeah,
That means
but
that
I didn't.
in this area, b theta is very small. Now, if we consider this point here, this is the tangential direction. And this is the radial direction. We are saying is that the velocity in the tangential direction, in this direction, is very small. Makes sense, because we're expecting the motion to be basically to the right. Let's check with VR. And with that, we're going to finish here. U0 squared minus all this in this area, in this region, well ahead of the body, the value of R will be very large. Can you evaluate this in this area? Anybody? What will you obtain in this area here? What will you obtain in this area?
Negative value.
The
R
maximum
is-
values of the
Just you.
Exactly, just you. Because R squared in the denominator is very high. So this value would be basically 0. What's the cosine of 0? Cosine of 0 is cosine of 0, people, come on.
1, doctor.
Is 1. So basically in this area, V sub r is u. So you have a body, let me draw here, very small. Away, you have this is u. Away, u. So that we are analyzing this area here. Well ahead of the body. And here, I do not expect any influence from this guy. Makes sense? So what we have to do is check, for example, in this area here, with a very large value of r, with a value of theta of about 90, we should check that the velocities basically should be only pointing to the right. And using this expression, we have to check. Okay, I'm sorry because it took me too much. I already sent you the second homework, the second assignment, and it's due next Thursday. Remember, next Thursday, you have to come to the university. We're going to do some tests in the lab, and you have to take the quiz number 1. Okay? Any questions about that? Any questions about that, people?
Doctor, the test, the quiz, and lab are in the same hours of the class.
No, no. The quiz is going to be in the same at the same time. Usually, I put it a little bit before 4. Okay, I'm going to post it right away, and then in another day you will have to take to do the lab. Yes. Also remember that homework 2, assignment 2, each one of you will have to make a short presentation on one of the problems in English. It's going to be fun. But you have to prepare a short video of one of the problems. You have to load it in the system, and then in a schedule that I will post, you have to make a short presentation on one of the problems of the assignment. Very short, don't worry. It doesn't, I mean, I'm not going to ask you to do a 10-minute presentation. I just want you to have, if you have in your hand the homework, okay, you can see some of that, and I want you to explain it to me. That's all. So all I need is to be sure that you're not copying the homework. That's all. Surprise. Okay, people, see you Tuesday. See you Thursday, sorry. Bye-bye now.